if you have followed our lessons in our previous lessons, we have introduced the reduction formula. In today's lesson, we'll use reduction formula to derive the integral for cos raised to power n. At the end of this lesson, we would have honed our skills on the reduction formula, integration by parts, differentiation of function of a function, and trigonometric identities. That said, let's get into class. Now, we want to use reduction formula to find the integral of in is equals to the integral of cos n, cos raised to power n, cos x raised to power n with respect to dx. Now, a simple way to express this function, you know that this function is of the form of, I can easily write this as cos n minus 1 dot cos x. Yes, cos x with respect to dx. Now, this is just simple indices. I know that in indices, if I have x raised to power n minus 1 times x, that will be the same thing as x raised to power n minus 1 plus 1, which is equals to x raised to power n. Now, that's the same thing we have done here. Now, if knowing that my in is of this form, now knowing that my in is equals to the integral of cos x raised to power n minus 1 cos x, I can easily use integration by parts to solve this. In integration by parts, I know that if I have the integral of u dv to be the same thing as uv minus the integral of v du. Now, so that here my u is the same thing as cos x raised to power n minus 1, and my dv is the same thing as cos x. Now, for cos x, this is quite easily done. For cos x, my v on integrating is equals to sine x. But for me to differentiate u to come up with the u, I'll need to use function of a function. Let's quickly do that by the side here. Now, if my u is equals to the cos of x raised to power n minus 1, I can say let z be equals to cos x. So that if z is equals to cos x, dz dx will be the same thing as minus sine x. Then my u will be equals to z raised to power n minus 1. So that du now, dz, du dz will be the same thing as n minus 1, this is minus 1 please, z raised to power n minus 1, that's n minus 2. So that du dz times dz dx will be equals to du dx, which is what we're actually looking for. If you remember what I just cleaned up, my du dz is minus sine x, this will be minus sine x multiplied by dz dx. My dz dx is here, obviously, that's into n minus 1 into z raised to power n minus 2. Remember that we assumed that z is equals to cos x. So that if I rearrange this, my du dx is the same thing as minus n minus 1 sine x. Then in place of z, I have cos x raised to power n minus 2. So in here, I can easily write this here. This is minus n minus 1 sine x cos x raised to power n minus 2. Now let's put into the formula for our integration by part. Now, so it becomes, remember I'm bringing in u dv, I'm bringing the integral of u dv to be equals to uv minus the integral of v du. Now, of the integral of cos n, the integral of cos n with respect to x will equals to u dv. My u from here is cos x raised to power n minus 1. My dv is cos x, or my u is cos x raised to, my u is cos x n, my u is cos x raised to power n minus 1, and my v is sine x. That will be sine x dot cos x raised to power n minus 1 minus the integral of, my v here is sine x and my du is minus sine x. That's sine x. Let me be sure I'm right. V is sine x and du is minus into minus 1. That's into minus into n minus 1 sine x cos x raised to power n minus 2. Sine x cos x raised to power n minus 2. It looks a little clumsy, but I'll try my best to make it as simple as possible. Now, so that the integral of cos n raised to power x will be the same thing as sine x cos x raised to power n minus 1. Now, I have negative here. It automatically becomes plus. Then I want to bring out this constant. That will be n minus 1 sine. Now look at, I have sine x here. I have sine x here. It becomes sine squared x. There's an integral sign here. Cos raised to power n minus 2 of x with respect to dx. Now we know that sine squared x plus cos squared x is equals to 1. So that sine squared x on its own is the same thing as 1 minus cos squared x. So I can now rewrite this, my cos x raised to power n, which is the same thing as in. Remember, this is our in because we're actually deriving a reduction formula. This will be the same thing as sine x cos x raised to power n minus 1 plus n minus 1 now, the integral of, now I have 1 minus cos squared x. I've put this formula in place of sine squared x here, multiplying cos x raised to power n minus 2 with respect to the x. Now, this, my in, let me just throw in in now, will be the same thing as sine x cos x raised to power n minus 1 plus, I want to expand this, and at the same time, I'll be multiplying it with two things. I'll be multiplying it with cos x raised to power n minus 2 and with n minus 1. So the first set will be cos x n raised to power n minus 2 minus, open another integral again. I have n minus 1 here again into, let me use bracket, into cos squared x dot cos x raised to power n minus 2. Now, if you begin to look at this, you look at this expression, this is forming another indices, just the same way we did with x the other time. Look at, let me just quickly solve that here. If I have x raised to power 1 times x raised to power n minus 1. Obviously, from my simple indices, this is x raised to power 1 plus n minus 1, which is x raised to power n. The same thing I'm going to apply here, so that my in can easily be written as the sine of x, the cos of n minus 1 plus n minus 1 now, integral of cos x, here is n minus 2 minus, now this automatically becomes cos raised to power n because this is 2 like I explained initially, and this is minus 2. Then I'll be left with n. That's n minus 1 integral of cos raised to power n of x. Now if you remember that our in is the same thing as cos x raised to power n. So in place of my cos x raised to power n here, I can begin to summarize my reduction formula. This is sine x. Look at this is cos n minus 1 of x plus n minus 1. Here I have integral of cos x raised to power n minus 2. I can summarize that to be cos to I n minus 2. Observe that I have cos x raised to power n minus 1 here. I did not summarize it to I n minus 1 because there is no integral sign here. It is not of the same form with my I n is equals to integral of cos x raised to power n. Now minus, I can put a bracket here, n minus 1 now. I have cos raised to power n here. Obviously, I can summarize this to in. I have in at this side. I have in at this side. I want to collect like terms so that it becomes in will now be equals to sine x. Let me just look at it again. This sine x cos x raised to power n minus 1 cos x raised to power n minus 1 plus n minus 1 into in minus 2 plus n minus 1 into in minus 2 minus n minus 1 again into in minus n minus 1 into in. Now let's call it that like that. So that in now plus n minus 1 into in will be the same thing as sine x cos x n minus 1 plus n minus 1 in minus 2. Now if you expand this in into n this is this, then minus 1 obviously this becomes n into in is equals to sine x cos x n minus 1 plus n minus 1 in minus 2. I can divide across board by n, can divide across board by n, so that my reduction formula comes out this way. In is equals to sine x cos n minus 1 plus n minus 1 over n in minus 2. I omitted something. This side is over n, so that I can write it as in. This will be 1 into sine x cos x n minus 1 plus n minus 1 over n in minus 2. In minus 2. Now with this, we have derived the reduction formula for in is equals to the integral of cos x raised to power n with respect to the x.